Hello and welcome to yet another episode in CSC 263 Database Management Systems at Adelphi University. Today we'll start introducing the Relational Database model. In the previous few videos we looked at data and data modeling. And the whole goal of those videos was to develop an understanding of what our data looked like, but from a conceptual level, which means a technology agnostic approach to understanding the data. And as good as it is to have an understanding about data that does not depend on technology, eventually we'll have to go implement it, and therefore technology decisions do need to be made. And that is what we start working towards in this video. This is based on the book. This is chapter 4 of the book, the Relational Model. So, as I mentioned, we have now started to develop an understanding of what our data looks like. We are starting to see how the different components of data interrelate and what properties the data has that we are storing. We need to be able to express that technology agnostic approach to data in a format that a computer can understand. And for that we use a database management system. Now, the thing is, database management systems are based on these computing paradigms. So we have to map our understanding of the data to whatever paradigm the database that we choose to use has embraced. And so, by far still the most common type of database that we see today is the relational database. The relational database was originally introduced in 1970, so let that sink in for a second. This is 2020. That means that this is a 50-year-old database model, yet it's still highly relevant today. And when we look back at our discipline, computer science, try to really find technologies or models, architectures that were created 50 years ago that we can still use today and that we are still using today. Just that by itself is an attestation to how well the relational database has worked out. One of the main reasons why the relational database model has been so successful is that it's easy to understand, and hopefully I'll demonstrate that in a second. But secondly, the relational database model is also based on some strong mathematical foundations, which means that we can do quite a bit of analysis and also proving that the database is correct. Now, we're not going to go into those mathematical proofs of the relational database as much, but we will be touching on the relational algebra a little bit in one of the upcoming videos. So they're easy to understand, they are based on a strong theoretical foundation, and lastly, there are some really good commercial implementations available. You can buy a relational database right off the shelf, and the only thing you have to do is tell it what data you want to store in there. It's not necessarily a difficult product to use. Doesn't mean it's an easy product to build, but it is one that you can easily use, and its use is also fairly well understood. Some of the well-known databases include Oracle, include Microsoft SQL Server, but also include databases like MySQL or MariaDB or PostgreSQL. PostgreSQL is really a next generation relational database. It's an object relational database, but it is the database that we will be using in class. It is free and open source software, so you can download it rather easily to your own computer, and there's no real restrictions on its use. The fact that it is an object relational database, we're going to kind of ignore, and we're just going to pretend like it's a relational database in its own right. So, having said that, let's talk about the relational model. Let's do an informal definition first. We're going to describe the things that we identified in our data model in key value pairs. So, for example, if I would be modeling, say, an inventory of pens, I can try to identify a number of attributes by which I am going to describe pens. And as I describe pens using those attributes, I give them actual values. So for example, I might have a pen that on the outside looks red. So that is a property. The color of the casing around the pen is red. But the ink in the pen is blue. So I have to be able to separately describe those. It is a type of pen. It is a fountain pen. It could have been a roller tip. It could have been a ballpoint, whatever it may be, a gel pen. But we want to be able to capture what kind of pen we're selling here. Maybe an overall type is not good enough. So for example, when you're dealing with fountain pens, you also need to know what kind of ink cartridges it will hold. So maybe you need a subtype as well. And maybe to list in our catalog, we might want to list a brand as well. Parker is one of those. And so we can start listing a whole bunch of these properties of these different pens that we want to be able to describe, and then the actual values that describe the pens. To a computer scientist who has trained in using, for example, objects and object classes and attributes in those objects, this should all be very intuitive and very easily understood. A collection of these key value pairs, that's then called a tuple, and not an object as we would know from programming, we call it a tuple. Now, that's informally. Let's look at it a little bit more formally. A relational database is logically structured in relations. A relation consists of one or more named attributes. So for example, I had my relation or the pen, and in that relation I had named attributes like the color of the case, the color of the ink, the brand, the type, and the subtype. Those were all named attributes. When I put those together to describe an actual pen, I have a relation. Each fact, so each actual pen, is then represented by something we call a tuple or a tuple, depending on how you want to pronounce it. And that contains values. One value for each of the corresponding attributes. So I might say, okay, this is a pen that writes blue. This is a person with last name Leune, if we're talking about those. And once we start putting those together, we have a fairly comprehensive model. So we have again the relations with the named attributes, and then we have the tuples who give values to those relations. Attributes are defined on a domain. That means for each attribute we maintain the name of the attribute, but we also maintain a list of all possible values that that attribute is allowed to take. From computer science, we know the concept of data typing. This is the same concept. We're going to say, okay, this can hold a number, or this can hold a text, or maybe this can hold an enumeration of values. We've done all of this in our programming languages. But keep in mind, this was 1970. This SQL concept predates many of the programming languages, or probably any of the programming languages that we routinely use today. So even though for us now the idea of having an object with attributes and a data type is really intuitive, when it came to putting together the relational database model, they were there first. The programming languages followed. So that another example to get all of these terms straight. Let's say that I have a relation called people or persons. I might put a name attribute in there, although later on we'll see why that's probably a bad plan. But that means that we're going to be allowed or able to describe a person by their name. We also have to define the domain, so in this case it could be just text, or maybe text up to 60 characters or text up to 80 characters. And we're going to add a value to describe an actual person whose last name is Leune. So separate out those two. On the one hand, we describe the relations with their named attributes and their domains. That is the metadata. And then the tuples, the tuples, contain the actual data, contain the values for each of those relations. Couple of Oxford terminology things that you need to be aware of. The degree of a relation is the number of attributes that a relation has. So if I only describe a person by name, it's degree 1. In the example we use for the pen, I had the case color, I had the ink color, I had the type and the subtype and the brand. That's 5. So those were degree 5. The cardinality of a relation is how many tuples are there of that relation. So if I have 10 different pens in my catalog, then I have a cardinality of 10. The superkey, and that's an important concept, is an attribute or a combination of attributes, it doesn't have to be just one, that can be used to uniquely and unambiguously identify a single tuple in the database. So if I have, for example, a relation with people, and I have for a person their first name, their last name, their date of birth, and their email address, I might say, okay, well, if I have first name, last name, date of birth, then I have a unambiguous record. It does mean that if I have two people who have exactly the same name and who have exactly the same date of birth, my database cannot distinguish between the two. But if that is okay in your model domain, then that's fine. The other thing could be, okay, let's go with just the email address. Now, the email address has to be unique, has to be able to unambiguously identify. All relations must have an attribute or a combination of attributes that can be used to unambiguously identify a tuple in that relation. So keep that in mind. Now, in the example I just gave you, we have, on the one hand, we could use a first name, last name, date of birth. That is a combination of 3 attributes. Or we could use email address. That is 1 attribute. What we say is that the minimal superkey is the smallest superkey we can create. So in this case, that would be email address. That is a superkey containing of only 1 attribute. So that becomes a candidate key. If I have the possibility to choose multiple candidate keys in a relation, at that point I can just arbitrarily pick one and say that is going to be my primary key. But every relation in the relational database must have a primary key. So it is a minimal superkey, and if I have multiple of those, I just pick one, as long as it's a small one. So those are some of the basic terms that I'll probably be using quite regularly throughout the rest of this course and that you need to be aware of. The relational database also imposes constraints. Some of those constraints are obvious, others maybe not so. Keep in mind that one of the main reasons for developing and using the relational database model is to ensure data integrity. I want to make sure that the data that's in my database is correct and that it stays correct. It means, and we'll talk about this soon when we talk about normalization, for example, that I don't want to record the same fact of data twice, because now I have to maintain it in 2 different places. By defining that on your database schema, you can probably do that. But the other way we can do that is by adding constraints. So for example, if I'm going to give someone a date of birth, putting a value of 24 green apples in there does not make a whole lot of sense. 24 green apples is not a date, and a date of birth has to be a date. That is called an integrity constraint. When I talk about, let's say, a student's GPA, and I put in green kiwis, again, it does not make a whole lot of sense. If I put in 26, it also doesn't make a whole lot of sense, because at least at Adelphi, the GPA ranges from 0 to 4.0. There's nothing less than 0 and nothing more than 4.0. If I can convey that kind of information to my database management system, then my database management system can enforce those integrity constraints as rules, and the risk that I get dirty data in my database goes down. There are 4 main integrity constraints that we see in the relational database model. Those are domain integrity, entity integrity, referential integrity, and what we call general constraints. And let's take a quick look at each of them. Domain integrity requires that all attributes must be defined on a domain and that the values in those tuples must match those domains. Sounds fairly obvious, but it basically says if I define a date of birth as a date, then my actual date of birth also has to be a date. Yeah. But this is something that the computer can enforce for us. And that basically eliminates a lot of data entry errors. So domain integrity. All attributes must be defined on a domain, and all values in the tuples must match the domain. Again, next example. Temperature readings. Let's say that I run a large collection of weather stations and I take readings from each of those weather stations. I probably want to timestamp those so that I know when I took that reading. And so I can put a data type, a domain, on the timestamp. I can, for example, say it has to be a date time with a time zone. Times and dates are actually very complex if you start really thinking about it. How many days have expired between January 15th and March 15th? Well, normally you'd say, well, that's 2 months, so that's about 60 days. Yeah, except when there's a leap year. So when there's there a leap year, for example, think about situations like that. And especially if you then also start factoring in time zones, dates and times become really difficult. But we might just have the database do that. We might just tell it that if you put a date in here, pretend like it's in the local time zone and combine the date with that time zone. I might have a definition that says that my station name is a textual description, what we call a variable character, of up to 80 characters, between 0 and 80 characters long. And I might define the temperature as a floating point number. And so my tuple becomes what you see on the slide behind me, 2019-09-15, that's the date, in an unambiguous notation, always year, month, date, the letter T, and then in 24-hour clock, the number of hours, minutes, and seconds, followed by plus or minus 0400, a 4-hour offset from the time zone. It is not a very friendly way to write this for human consumption, but the computer can make easy sense of this. And so I can easily represent that. The second integrity constraint is the entity integrity constraint. It says that all relations must have a primary key. So that means that we need to identify the superkeys, pick the minimum superkeys, and then from those minimum superkeys identify one that we're going to call the primary keys. It also says that if an attribute is part of the primary key, or is by itself the primary key, then it cannot be empty. It must always hold a value. Makes sense because I'm using that to unambiguously identify the tuple, so there should be a value there. But what it also says is that value has to be unique to the relation in that attribute. I cannot have two attributes with the same value, and again, that makes sense, or with the same primary key, because I'm using it to unambiguously identify. And so, all attributes must have a primary key, all attributes of the primary key must have a defined value, and each value on a primary key must be unique. Keep in mind, footnote, that there is a special value in a database called null, N-U-L-L, and that means I don't care or I don't know, undefined. The null value matches with all domains. So I can have a null date, and I can have a null string, I can have a null number, I can have all kinds of nulls. Entity integrity basically then says primary keys must be not null and unique, and we'll see those at a later point. Example again, the primary key in the temperature readings relation is the combination of timestamp and station name. It means that I can now not define any readings that don't have a known time or a known location, but it also means that at a specific time and a specific location, the combination of those two, I only can record one reading. Choosing a primary key is important, but you have to be careful when doing it. Referential integrity means that I can have multiple relations that point to each other. For example, if I'm going to take a student who wants to register for a class, I want to know that the student exists and that the class exists. So in that registration entry, I want to make sure that I'm only putting students in there who also exist in the students relation. And I also want to make sure I only put courses in there that exist in the courses relation. That's called a foreign key relationship. And so in this particular case, the referential integrity rule enforces those foreign keys. It means that if I define one of those foreign key relationships, then they have a source and a destination. So for example, in my courses table, if I define my course registrations table, if I define a foreign key to students, I cannot put a value in the registration if the student I reference in it does not exist in the students table, or the course does not exist in the courses table. More formally, it says that if I define one of those foreign key relationships, the foreign key must be present in the target relation, or all of the foreign key must be null. I'm allowed to keep the foreign key as null. That's fine, as long as the entire foreign key is null, because then it doesn't reference anything. But the table that I'm pointing to, that attribute in there, or the combination of attributes in there, that have to be a candidate key on that relation. Sounds very abstract. We'll refer to this quite a little bit more down the road, and it becomes probably more practical and more understandable at that point, but we need to introduce it here. And then we have general constraints, which means anything else. So for example, if I'm going to record a temperature in Garden City, I might tell my database, well, if your temperature drops below -30 degrees Celsius or goes above 50 degrees Celsius, something is really wrong and you should not accept that value. I might say that if a student puts in a date of birth before 1900, we can't have that. Well, bad example, Adelphi probably does have a few students from the late 1800s, but before 1700, whatever we want to put in there, we can put a cutoff in there. And that is of course all for data integrity purposes. So that's the relational model. In summary then, the relational model consists of relations. Each relation consists of named attributes that are defined on a domain. Each relation must have an attribute or a combination of attributes that uniquely identifies all of the tuples in that relation. The tuples represent the actual values. The minimal tuple that uniquely identifies, the attribute or the combination of attributes that uniquely identifies the tuple is called the superkey. The minimal superkey is called the candidate key, and any of the arbitrarily chosen candidate keys can become the primary key. We have integrity constraints, entity integrity, referential integrity, we have domain integrity, and we have the check constraints or the general constraints. Each one of those are enforced by the RDBMS, and the more of those constraints that I can specify up front, the better off my data integrity will remain in the long run. Okay, so that's the basic overview of the relational model. We'll dig into this deeper in class when we do some hand-on exercises, but for now, that's it.